Hello everybody. In example 3 on page 126, we are going to look at another example where we are finding an interval of convergence of another power series. All right, we already have done this now a couple times, so let's start right away by using the ratio test to figure out what's going on. So using the ratio test, we get the limit as n goes to infinity of an plus 1 divided by an, an absolute value. And that is the limit as n goes to infinity of, let's see, x minus 2 to the n plus 1 divided by 2 to the n plus 1 times the square root of n plus 1. Okay, and then we divide by an, and again multiply by the reciprocal instead. So we have 2 to the n over the square root of n in the numerator and x minus 2, to the n in the denominator. And this looks a little intimidating maybe, but just like before, lots of stuff is going to cancel. So when you look at the x minus 2 to the n plus 1 term and the x minus 2 to the n term, the same thing happened that we saw in the previous examples. Most of those factors cancel and we are left with x minus 2, which we can pull out in absolute value out of the limit. And then we are left with the limit as n goes to infinity. And let's look at the 2 to the n. We have 2 to the n, and then we have 2 to the n plus 1. That also simplifies. All that's left is really a 2 in the denominator, and that we can also pull out because that's a constant and just write it underneath that x minus 2 in absolute value. And then all that we are left with really is the absolute value of the absolute value of the square root of n over the square root of n plus 1. And here we can drop the absolute value and we can also simplify, but write it as one big absolute value. So we have x minus 2, an absolute value, over 2, limit as n goes to infinity, and then we have one big square root n over n plus 1. And rules of limits allow us to even pull that square root outside of the limit. So this becomes x minus 2 over 2 absolute value times the limit of n over n plus 1, limit as n goes to infinity, and then that whole limit is under the square root. And this is nice, this is convenient, because now we can compute the limit of n over n plus 1. And actually we did that in the previous example. We already know what that is. This whole limit using L'Hopital's rule is just equal to 1. And so we can say, by L'Hopital's rule, this whole thing becomes the absolute value of x minus 2 divided by 2. That is our value of r from the ratio test. Okay, when do we get convergence? Well, we get convergence when x minus 2, an absolute value, divided by 2 is less than 1. And our goal is to be able to describe the values of x. So we need to solve this inequality for x. So first thing we can do is multiply both sides by 2 to get the absolute value of x minus 2 is less than 2. And then we rewrite it again by saying x minus 2 has to be less than 2, but it also has to be greater than minus 2. And then one more step, we can add 2 to each term to get x by itself. So this gives us 0 is less than x is less than 4. Okay, so we can conclude that our series converges when x is between 0 and 4. 0 less than x less than 4. That doesn't tell us anything about the endpoints, so we have to look at the endpoints separately. Okay, so our endpoints are x equals 0 and x equals 4. So let's examine our series at those points separately. When x equals 4, if you look at your notes, the series is n goes from 1 to infinity, and we had x minus 2 to the n, so we have 0 minus 2 to the n, that is minus 2 to the n, divided by 2 to the n times the square root of n. That simplifies quite a bit. We can rewrite this as n goes from 1 to infinity of minus 1 to the n times 2 to the n. And in the denominator we have a 2 to the n and the square root of n. And I did this so that we can cancel the 2 to the n's, and we just have n from 1 to infinity of minus 1 to the n divided by the square root of n. And that is, what kind of a series is that? Right, this is again an alternating series. With bn equal to 1 over the square root of n. And the two conditions work. Bn, the limit as n goes to infinity of bn is going to be 0, and bn plus 1 is less than 1 over the square root of n, so this is actually going to converge. We're going to write that down in a minute after we look at the second endpoint, x equals 2. Okay, oh, not x equals 2, sorry. We have x equals 4 in this case. So when we plug in x equals 4, we have the series n goes from 1 to infinity of 4 minus 2 to the n divided by 2 to the n square root of n. And that is the series n goes from 1 to infinity of 2 to the n divided by 2 to the n square root of n. And again, the 2 to the n's cancel. So we have the series of just 1 over the square root of n. And that is also should look familiar. And I give you a second to think about what type of a series this is. This is a p-series with p equal to 1/2. So that is divergent. So we have a convergent alternating series at one endpoint at x equals 0, and we have a divergent p-series at x equals 4. So we should write down, we're almost ready to write down our conclusion, but let's write down again the little mini proof that the alternating series converges. So we have the alternating series sum minus 1 to the n over the square root of n converges since the limit as n goes to infinity of 1 over the square root of n is equal to 0, and 1 over the square root of n plus 1 is less or equal to 1 over the square root of n for all n greater or equal to 1. All right, So therefore, we have convergence at x equals 0, divergence at x equals 4, and so our final answer for our interval of convergence is closed interval at 0, open interval at 4. Or if you like, you can also write it as 0 is less or equal to x is less, strictly less than 4.